After studying this module, you shall be able to know briefly about the distribution of molar mass of polymer, learn about different formulas for calculating average molar masses of polymers, compare number average molar mass and weight average molar mass. Polymers or macromolecules are the long chain high molecular weight compounds formed by the combination of a large number of simple molecules. The simple molecules taking part in the formation of polymers are called monomers, and this process of polymer formation is called polymerization. The product formed is either a dimer, trimer or tetramer depending upon the number of molecules combining 2, 3 or 4 molecules respectively. If large number of molecules combine together, then the product is called as a polymer. Example, polyethylene polymer is obtained by combining n number of molecules of ethylene. The number of repeating units in the polymer chain is called the degree of polymerization. The product of degree of polymerization, that is N, and the molecular mass of the monomeric unit M is equal to the molecular mass of the polymer. Mathematically, molecular mass of the polymer equals to N multiplied by mm. Now we shall see the classification of polymers. It is shown in the given flow chart. Polymers are replacing metals. The reason behind this approach is design freedom, the elimination of many secondary operations. Moreover, metals are prone to corrosion while the polymers are not. Some of the key benefits of replacing metals with polymers include weight reduction up to 80%. They are lightweight as they are composed of carbon, hydrogen, oxygen, nitrogen, etc. as the basic atoms. Faster installation, that is, they are easy to process. They have greater workability. They have 5 times higher mechanical properties. Examples include polyaniline, polythiophene, polypyrrole. Polymer molecular weight is essential as it helps in determination of many of its physical properties like mechanical properties such as strength, viscosity, etc. Strength is too low for polymer to be used when it has low molecular weight. When the polymer has high molecular weight, the strength increases, saturating to infinite molecular weight. The molar mass of polymers increase on condensation or addition reaction. Since at different stages of polymerization chains are broken, resultant macromolecules do not have the same molar mass. That is, macromolecules do not have unique molecular weight. In linear polymers, individual polymer chains do not have the same degree of polymerization and molar mass and is always near an average value. Therefore, same molecule may have different molecular weight depending upon method by which the macromolecule is produced. Hence, distribution or average of molecular weight is used. In this module, we will be considering different ways of calculating molecular weight of the polymers. Now, we shall have a look at the molar mass distribution. There are different ways of expressing molar mass of polymers. Some commonly used averages are as follows: number average molar mass, mass average molar mass, viscosity average molar mass and Z average molar mass. Looking at the number average molar mass, consider a polymer sample which has N1 number of chains of monomers having the molar mass M1, N2 number of chains of dimers having molar mass M2. Similarly, there are in general Ni chains of imers with the molar mass Mi. Number average molar mass is obtained by carrying out the summation over the fraction of molecules multiplied by their corresponding molar mass, that is, mathematically it can be seen as given by equation 1, Mn bar, which is the number average molar mass, is given by summation I Fi Mi, where Mn bar is the number average molar mass. The fraction Fi is given by Fi equals to Ni by N total, equation 2, where Ni is the number of molecules having molar mass Mi and N total is the total number of molecules present in the polymer sample. Also, N total is summation I Ni. This is our equation 3. Substituting equation 2 in 1, we get Mn bar equals to summation I Ni by N total into Mi, which can be further simplified as summation I Ni Mi by N total as our equation 4. Substituting equation 3 in equation 4, Mn becomes equal to summation I Ni Mi divided by summation Ni. This is our equation 5. The expression for number average molar mass in terms of number of moles and number fraction can be derived in the following manner. Figure 1 shows the polymer sample containing Ni chains of imers. Consider a sample of polymer, N1 molecules having molecular weight M1 each, N2 molecules having molecular weight M2 each, N3 molecules having molecular weight M3 each, and so on. Then we have total molecular weight of all the N1 molecules equals to N1 M1, total molecular weight of all the N2 molecules equal to N2 M2, total molecular weight of all the N3 molecules as N3 M3. Therefore, the total molecular weight of all the molecules becomes equal to N1 M1 plus N2 M2 plus N3 M3 plus so on, which is equal to summation Ni Mi. Total number of molecules is equal to N1 plus N2 plus N3 plus so on equals to summation Ni. Therefore, from the definition of number average molar mass, we have Mn bar equals to N1 M1 plus N2 M2 plus N3 M3 plus so on divided by N1 plus N2 plus N3 plus so on. This is our equation 6. Dividing equation 5 by N, we get Mn bar equals to summation I Ni by N into Mi divided by summation Ni by N. This is our equation 7, where N is the total number of chain of all types in the sample. N is equal to N1 plus N2 plus N3 plus up till Ni. Therefore, Mn bar is equals to summation Ni by N into Mi divided by N, which can be written as Mn bar equals to summation chi Ni into Mi as our equation 8, where chi Ni is the number fraction. Dividing equation 5 with Na, we get Mn bar equals to summation Ni by Na into Mi divided by summation Ni by Na, which is equal to summation Ni Mi divided by summation Ni, where N is the number of moles. This is our equation 9. In certain experiments, it is easier to measure the weight of polymer instead of number of molecules of a polymer. Therefore, it is useful to derive alternative form of Mn in terms of weight fraction of polymers, mole fraction of polymers. Most of the thermodynamic measurements are based on the number of molecules present and hence depend on the number average molecular weight. For example, the colligative properties, which include osmotic pressure, freezing point depression, elevation and boiling point, relative lowering of vapor pressure. Colligative properties depend only on the number of molecules present and not on the shape of the molecule. Therefore, the number average molar mass is the most relevant average molar mass. Colligative properties are used for polymers because they are non-volatile. We should note that Mn values are independent of molecular size. Mn values are determined by Raoult's techniques that are dependent on colligative properties, which are ebullientiometry, that is the boiling point elevation, cryometry, which is the freezing point depression, and the osmometry. Mn can also be determined by gel permeation chromatography, viscometry, endpoint determination, or the proton NMR. Now we should look at the weight average molar mass. Weight average molar mass is the different way of describing molar mass of a polymer. There are certain properties which not only depend on the number of molecules but also on size and weight of each polymer molecule. Such properties include sedimentation, light scattering, diffusion, etc. Since the properties are dependent on the size of the molecule, so larger the molecule, greater will be its contribution in calculation of MW as compared to the smaller molecule. When the total molecular weight of group of molecules having particular molecular weights are multiplied with their respective molecular weights, the products are added and the sum is divided by the total weight of all the molecules. The result obtained is called the weight average molecular weight. Mathematically, weight average molar mass can be represented as mW bar equals to summation Wi Mi by Wi as given by equation 10. Dividing equation 10 by W, where W is equals to W1 plus W2 plus W3 up till Wi, which can be further written as summation Wi. Therefore, we get mW bar is equals to summation Wi by W into Mi divided by summation Wi by W. This is our equation 11. Or mW bar is equal to summation chi Wi into Mi, where chi Wi is the weight fraction equal to Wi by W. This is our equation 12. Since Wi can be written as Ni by Na into Mi in terms of number of moles, weight average molar mass can be written as mW bar is equal to summation Ni Mi square divided by summation Ni Mi as our equation 13, where N is the number of moles. In terms of number of molecules, weight average molar mass can be written as mW bar is equal to summation Ni Mi square by Na divided by summation Ni Mi by Na, or mW bar can be written as summation Ni Mi square divided by summation Ni Mi as our equation 14. As Wi is equals to Ni into Mi by Na, using this we get mW bar equals to summation Ni Mi by Na into Mi divided by summation Ni Mi by Na, which can be written as summation Ni Mi square divided by summation Ni Mi as equation 15. In terms of fraction of molecules, that is Fi, mass average molar mass is written by mW bar equals to summation Fi Mi square by summation Fi Mi as equation 16. The mW can be determined by various techniques like X-ray scattering, sedimentation velocity, static light scattering, and small angle neutron scattering. Now we shall look at the Z average molar mass. The Z average molar mass is the third power of the molar mass and is defined by the formula mZ bar equals to summation Ni Mi cube divided by summation Ni Mi square as our equation 17, where Ni is the number of molecules, Mi is the respective molar mass of the molecules. Since in this average weighing factor is Ni Mi square, that is dependent of weight, therefore heavier the molecule, greater will it be its contribution in calculating mZ. Now we shall have a look at the viscosity average molar mass. The viscosity average molar mass is defined as mV bar equals to summation Ni Mi to the power a plus 1 divided by summation Ni Mi whole raised to the power 1 by a as given by equation 18, where a is the constant and is dependent on the polymer or the solvent pair used in the viscosity experiments. It lies in the range of 0.5 to 1. The constant A is known as Markov exponent. The viscosity average molar mass is not absolute value, but a relative mass based on prior calibration with known molar mass for the same polymer solvent temperature conditions. Now we shall have a look at the polydispersity index. The most important property of a polymer is its heterogeneous character. A polymer sample will contain chains of different lengths. Two polymeric samples made from the same monomeric cannot be identical, so the molar mass of the polymer cannot be exactly defined and it varies from sample to sample. This property of a polymer of possessing different chain lengths in a sample is termed as polydispersity. Monodispersed substances have only one value of molar mass, example water or alcohol. Systems which has a range of molecular weights, such systems are called as polydispersed. Polydispersity index is the measure of the distribution of molecular mass of the polymer molecules in a given sample, and any system having the range of molecular weight is said to be polydispersed. In other words, PDI is used as a measure of the broadness of molecular weight distribution of a polymer. PDI is the ratio of mass average molar mass and number average molar mass. That is, PDI is equals to MW by Mn, where MW is the mass average molar mass and is more sensitive to molecules having higher molecular mass. Mn is the number average molar mass and it is more sensitive to molecules having low molecular mass. Conditions when number average molar mass is equal to mass average molar mass, that is Mn is equals to Nw. Mn bar is given by N1 M1 plus N2 M2 plus so on divided by N1 plus N2 plus so on. Mw bar is equals to N1 M1 square plus N2 M2 square plus so on divided by N1 M1 plus N2 M2 plus so on. If Mn bar is equals to Mw bar, then N1 M1 plus N2 M2 plus so on divided by N1 plus N2 plus so on becomes equal to N1 M1 square plus N2 M2 square plus so on divided by N1 M1 plus N2 M2 plus so on. The two sides, that is the left hand side, will be equal to right hand side only if M1 is equal to M2 is equal to M. That is, all molecules should have the same molecular weight. In such case, average has no significance. For a monodispersed sample where all the chain lengths are equal, Mn bar is equals to Mw bar. Mn bar is equals to summation Ni by summation Ni equals to N into M by N, which is equals to M. And Mw bar is equals to summation Ni square divided by summation Ni, which is equal to N into M square divided by N into M equals to M. Therefore, for a monodispersed sample, example water, Mn bar is equals to Mw bar equals to M, the molar mass. Thus, PDI equals to Mn bar by Mw bar equals to M by M equals to 1. For a polydispersed sample, Mw bar will be greater than Mn bar. That is, summation Nimi square by summation Nimi will be greater than summation Nimi by summation Ni. Let I equals to 1 and 2 only. Then N1M1 square plus N2M2 square divided by N1M1 plus N2M2 becomes greater than N1M1 plus N2M2 divided by N1 plus M2. Or N1M1 square plus N2M2 square divided by N1M1 plus N2M2 minus N1M1 plus N2M2 divided by N1 plus M2 is greater than 0. Or we have, that is, N1 N2 into M1 minus M2 whole square is greater than 0. since n1 and m2 are always positive and m1 minus m2 whole square is always positive as it's a square term. Therefore, mw bar is greater than mn bar. Moreover, for a polydispersed sample, mw bar by mn bar is greater than 1. PDI has the value equal to or greater than 1. It cannot have value less than 1 because mw can never become less than mn. But as the polymer chains approach uniform chain length, PDI approaches to unity. That is, when the distribution of molecular weight in polymer sample becomes narrow, under these circumstances, mw becomes equal to mn. Larger the PDI, broader will be the molecular weight. Now, we shall compare the Mn and the Mw, that is the number average molar mass and the weight average molar mass. Number average molar mass, i.e. Mn, is just the arithmetic mean of all the molar masses, whereas the weight average molar mass, Mw, is the sum of the fractional masses that each molecule contributes to the average according to the ratio of its mass to that of the whole sample. In number average molar mass, each molecule counts equally to it. In weight average molecules contribute according to their respective masses. Colligative methods give the number average molecular weight, whereas the sedimentation techniques, light scattering techniques and ultracentrifugation techniques give the weight average molar mass. The number average is very sensitive to changes in the weight fractions of low molecular weight species. Weight average is very sensitive to changes in the weight fractions of high molecular weight species, as in the case of light scattering techniques, larger molecules contribute more as they scatter more light effectively. Now we shall see the molecular weight distribution. The most important feature distinguishing polymers from low molecular weight species is the existence of a distribution of chain lengths and therefore degrees of polymerization and molecular weights in all known polymers. This distribution can be illustrated by plotting the weight of polymer of a given molecular weight against the molecular weight. Figure 2 shows the distribution of molecular weights in a typical polymer. When the molecular weight distribution of polymer sample is narrow, the value of Mn approaches to that ofMm. That is, narrower the molecular weight range, closer will be the values ofMm and Mn. Moreover, heavier molecules contribute more to Mw than the lighter ones. Mw is greater than Mn except for a hypothetical monodispersed polymer. The value of Mw is greatly influenced by the presence of high molecular weight, just as Mn is influenced by species at the low end of the molecular weight distribution curve. Thus, the ratio of Mw by Mn gives the indication of breadth of molecular weight range in polymer sample, and this parameter is most often quoted for describing this feature. Now we shall see a numerical problem explaining the concept of Mn and Mw. Example 1. A sample of polymer consists of two components present in equal masses, one having M1 equals to 30 kg per mole and the other having M2 equals to 12 kg per mole. Calculate the mass average and the number average molar masses. The solution is as follows. The given is the molecular weights of the two polymers M1 as 30 kg per mole and M2 as 12 kg per mole. Therefore, we can calculate the mass average Mw bar and the number average Mn bar molar masses using the formulas as given by equation 1 and 2. We are also given that the sample contains equal masses of the two components, that is W1 is equals to W2. Therefore, from equation 1 we get Mw bar equals to M1 plus M2 by 2. Substituting the values, we get Mw bar equals to 21 kg per mole. Now we have to calculate Mn bar. We know W is equal to N multiplied by M, where N is the number of moles and M is the molecular mass, or W is equal to N by Na times M. or N is equal to W by M into Na as our equation 3. Using equation 3 in 2, we get Mn bar as, again we have W1 equals to W2, therefore Mn bar is equals to 1 plus 1 divided by 1 by M1 plus 1 by M2, which becomes Mn bar equals to twice M1 M2 upon M1 plus M2. Substituting the values, we get Mn bar equals to 17.14 kgs per mole. From the two results, we also get to know that Mw bar is greater than Mn. Example 2. A polydispersed sample of polystyrene is prepared by mixing 3 monodispersed samples in the following proportions: 1 gram 10,000 molecular weight, 2 grams 50,000 molecular weight, 2 grams of 1 lakh molecular weight. Using this information, calculate the number average molecular weight, weight average molecular weight, and the polydispersity index of the mixture. The solution is as follows. We can calculate the mass average Mw bar and the number average Mn bar molar masses using the formulas 1 and 2. Therefore, on substitution, we obtain Mn bar equals to 31,250 and Mw bar equals to 62,000. Polydispersity index equals to Mw bar by Mn bar is obtained as 1.98. Now we shall summarize what we have learnt in the module. Polymers are the mixtures of molecules that have different molecular sizes and weights. Therefore, there is a need to find their molecular mass averages. There is a dependence of the types of averages obtained through experiments on chemical and physical properties of the molecules involved. Hence, number average molar mass can be calculated by measuring the colligative properties. Likewise, mass average molar mass can be calculated by light scattering measurements. Various molecular mass averages lie at the different point of molecular mass distribution of a polymer. If the polymer has identical molecules, then all its molecular mass averages would be identical. Weight average molar mass is always greater than the number average molar mass. The width of the molar mass distribution of polymer is determined by calculating polydispersity index, that is Mw bar by Mn bar. If the value of the polydispersity index is close to 1, narrower will be the polymer's molecular mass distribution.